So for the second talk of today, we have Antoine, who is like a PhD student of Christian, and who's going to talk a bit about insufficient Gibbs sampling.
Okay. Okay, hi everyone. So thank you, Antonio, for having me and organizing this nice seminar, and thank you everyone online for attending to the seminar. So my name is Antoine Luciano. I'm a second year PhD student under the supervision of Christian Robert and Robin Ryder at Université Paris-Dauphine. And today I will present you my first PhD project, which is called Insufficient Gibbs Sampling, which is obviously a collaboration, a joint work with Christian Robert and Robin Ryder. And the preprint is on arXiv, and it will be soon published. It has been accepted to a journal, but you can check to the preprint on arXiv. So I don't know if I'm speaking to only to Bayesian statisticians, so I will do some kind reminders. So just let's recall the Bayesian framework. So let's put ourselves in a parametric framework. So we suppose that our data comes from a parametric distribution with a likelihood that we denote F. And we consider the prior knowledge that we have about our parameters as a prior distribution denoted P. And so we suppose that let's assume that we observe some data, and the goal of the Bayesian inference is to compute or to sample from the posterior distribution, which is basically the product of our prior knowledge, so the prior distribution P, and the information given by the data that are denoted by the posterior. And there is also this normalizing constant to have a distribution and thus density. And we'll go back to this little constant later in the talk. So let's now consider a different framework, which is the framework we put ourselves during this work. So again, it's a parametric framework. We have our parametric distribution. We have our prior. But for some reason, we suppose that we don't have access to our data, and the only thing that we have access to is robust statistic denoted Ty. And so the observation is T0, one realization of those robust statistics. And so we would like to sample from the posterior distribution given our data, but we don't have access to it. So our goal is to sample from the posterior distribution given what we have, and what we have are that robust statistics. So here to be clear, the word robust stands for quantitative robustness. So basically it's robustness to outliers. So basically during our work, we considered the statistic based on other statistics such as median, quantiles, or the MAD, but I will talk about it later. So the motivations of this work were twofold. The first one was more applied, more practical, because in many cases, for some privacy reasons, the data are not fully disclosed, but only an aggregated version of those data are disclosed. So that's the case for the income data. You, as a normal guy, you will never have access to a data set of income at the individual scale. You will have access to aggregated version of it. So for example, in France, we have this database called Philosophy, which is the database of income in France in every commune. So it's a division of the country. And for each commune, we have access to the quantiles of the income population. So there was obviously some previous work about quantile matching MCMC, but our contribution is quite different, and I will go back to that later. But the main motivation was more theoretical, because in the ABC literature, as I said, those robust statistics are by definition insufficient. So this posterior distribution is typically intractable. So it's a good example for the ABC methods because they are really useful in that kind of framework to do inference. But again, because I'm talking not only to Bayesian statistician, I will remind you what is ABC, what ABC is. So ABC stands for approximate Bayesian computation. And now let's suppose that we are observing some robust statistics. The simplest form of ABC to perform inference on the parameter theta will be with an algorithm of that form. So at its name let's imagine it's really simple, really simple. So the idea is quite simple. You just have to sample some parameter from the prior distribution. With that parameter that you just simulated, you will generate some data. And then you will just compare the statistic of your simulated data sets to the observed ones. And if they are close enough, you will accept the value of theta, or otherwise you will resample it again and again and again. So by close enough, I'm meaning that the distance between the two, so taking the norm that you like, you just have to have a distance between your two data sets, which is lower than epsilon. So the A of ABC stands for approximate, because with that kind of algorithm, you're not sampling from the posterior, but you're sampling from an approximation of this posterior. So this epsilon is also called, so this threshold is called the ABC error. And this approximation of the posterior, called a pseudo-posterior, can be really different from the exact posterior because of its epsilon. In a perfect world, we would like to perform ABC with ABC equal to 0, but it's never the case, because when you're decreasing epsilon, your computational cost increase a lot. So you will have to be satisfied with this pseudo posterior. So now let's go back to our framework. So we would like to sample from the posterior given some statistics. So now let's considering the joint distribution of the parameters and the data. So here the data play the role of a latent variable. And when we express the joint density of the parameters and the data, you can decompose it with two terms. And these decompositions led us to a well-known framework introduced years ago by Tanner and Wang, which is called data augmented MCMC. And the steps are quite simple. First, we will sample from augmented data from the given our robust statistics. So here, to make sure that you understand, we have to sample augmented data that perfectly match the observed statistics. And then we can sample from the classical, if I can say so, posterior distribution given our augmented data. So this framework has already been considered in the literature by an American student 3 years ago. And so we implemented a similar Gibbs sampler. And again, even if the Gibbs sampler is quite famous in the literature, I will quickly introduce the Gibbs sampler. So the Gibbs sampler is, idea is quite simple. When you have like here a J dimensional parameter, and you want to do inference on each of its components, so you want to compute the joint posterior of all the components of your parameter, you will like split your problem into smaller problems. So you will split your posterior into conditionals. And if you can sample from these conditionals, you can just update each component one at a time. thanks to from this conditionals. So I will go maybe faster because I think that everyone knows the Gibbs sampler. So with the data augmented MCMC framework, we can have this kind of Gibbs samplers. So just to make sure, we just initialize a data set that match the observed statistics. We arbitrarily initialize our parameter. And then at each iteration, we will just like update our data set, and then you update our parameter one at a time. So just to make things clear, the main challenge of this work was to propose a methodology to sample, so to update our data sets while preserving the observed statistic unchanged. So basically, it's to sample a Y from a parametric distribution in the constrained data space that we have to match the observed statistics. Do I have any question for? No, it's okay. Cool, it's okay. Okay, so during this talk, I will quickly present the methodology that we presented in the paper. So we considered 3 cases, so the quantile case, the median and interquartile case, and the median and the MAD case. Then I will give some numerical results and talk about Bayesian model choice, because one important thing of this work is that even with some insufficient statistics, so for example, in the Gaussian case, if you just observe the median and the MAD, you can perform some Bayesian model choice in some with some condition, under some conditions. So first, let's consider the case when we observe M quantiles. So here we just observe a vector of size M, which represents the quantile of our distribution. And in a really naive way, we can just like have this theoretical apportionment of our data. So I'm pretty sure that your little brother or little sister can make it. So we can just split our support into a partition of M+1 interval. And we know that we will have the following proportion in each interval. So basically, if we observe the first quantile, we know that we have a proportion P1 of data that are lower than its point, and then we can do it recursively to have this partition of the support and having this theoretical apportionment. But one thing about this approach, which is used in the previous work that I found in the literature, is to suppose that the quantile that we observe are theoretical quantiles, so that are quantile from distributions, but they are not quantile from a distribution, they are empirical quantiles. So basically, we have an underlying data set that we don't observe, but this data set exists, and the institution, for example, INSEE, just computed some empirical quantiles from the data set and published them. So the quantile that we observe are not theoretical, but empirical quantile. So there is a lot of different estimator of quantiles that exist in the literature. We decided to consider the most used one, which is used by default in R, Julia, and NumPy. This estimator is quite simple. I will be quick on this one. So it's just a linear combination of 2 order statistics. So for example, in the median case, so let's say that we have an odd data set, so a data set of odd size. If you observe the median, so the quantile 0.5, 50%, the quantile 50% of your data set, the median. In the odd case, the estimator will be fully deterministic, because in the odd case you will have like one observation which is exactly equal to the median, and if you are in the even case, it will be a G which is positive, and then you will have this linear combination. So here the thing that we want to do is to propose a Markov kernel to resample our data while preserving this empirical kernel. So the methodology that we propose in the paper is quite simple and is to first resample the order statistic that determine the quantile. So here I did a little tick figure to make sure that everyone is following. So let's say that we just initialized a vector with the observed quantile. So we initialized really naively a vector that have the same quantile that the one we observed, the empirical ones. And let's say now that you want to update this vector to go basically from yt to yt plus 1, the first step that we'll do is to update the order statistic. We decided to update only randomly the lower ones. Then with this updated order statistic, we can have the second ones that determine the quantile. So with a just deterministic transformation between Q and this order statistic, so we can get the other order statistic that determines the quantile. And then we just have to complete our vector with a truncated distribution, putting the right number of observations in each interval.
Can you go to the previous slide?
Yeah, which one?
This one, like yeah. G is
so G is like the weight between the linear combination.
Okay.
And if you are lucky, so for example, in the median case, in an odd case, G will be equal to 0.
Okay, so G depends on the statistics
you're
looking at.
It's fully deterministic on the size of your vector and the order the value of P, so the quantile P.
Okay. Okay.
And so in most of the case, you will be a positive G because your quantile is determined by 2 order statistics. In that case, the methodology that we propose is just to sample one order statistic and the second is fully deterministic.
Okay.
So the interesting part is just about the metropolis hastings kernel, but we can really simply, we can just like having we can know the joint distribution of our order statistics thanks to this formula, and then just running Markov chains that are targeting these distributions and sampling our order statistic and just complete the vector with truncated distribution. So this first case is quite simple, and the second one is also simple because it's really close from the quantile case. We just consider the case when we observe the median and the interquartile range, which is the difference between two quartiles. And so with the general framework that I just presented, we can just like adapt it to have this framework done. So it's explained in the paper. I don't think it's really worth it because we don't have so much time, so I will just keep it. So now let's talk about the most challenging, if I can say so, scenario that we presented in the paper. So it's the case when we observe the median and the MAD. So I think that everyone knows the median, which is the most used robust statistic. But its cousin, if I can say so, is less known. So it can be the median. The MAD stands for median absolute deviation. It can be seen as a robust alternative to the standard deviation, and is defined as the median of the distance to the median. It can be a little scary, but it's not at all. So if we just like summarize the two constraints that we get having those two observations, so the median and the MAD, the first constraint is quite simple. It's given by the median. We want to have half of our observation that are lower, the other half greater than the median. And basically the constraint given by the MAD, it's quite simple. We want to have half that of our observation that are in that interval. So here, if we are just like combining those two constraints, we end up with a 4-interval partition of our support and this theoretical apportionment, which is determined by this little p. So for example, if p is equal to 0, we will have all our data points in the zone, the interval 1 and 3. And if p is equal to 1/2, we'll have all our data points in zone 2 and 4. So it was the theoretical part, the more abstract part, just like let's apply it in the odd case, because the odd case is simpler. So in the odd case, we are lucky. We have one observation which is exactly equal to the median. We have one observation which is at a distance mad of the median. So because we have an odd size vector, we know that we have one observation which is or in m plus s or in m minus s, and we introduce this delta, this random variable delta that captures the position of this observation, and then we can just adapt the previous repartition between those 4 intervals with the little p with a more technical manner, so we can have this exact apportionment between our 4 intervals. So basically, if you have to just to summarize what we just learn, is that we know exactly the apportionment of our vector, but we don't know the value of k or delta. But basically, if you want to update, what we are searching for is to update, to have a Markov kernel that update at each iteration our vector. But to do so, we would like to have a way to have the law of k and delta, but we don't know it. So just to make things clear, so we have this representation, and as I said, the value of k is really important because the 2 datasets that I'm showing with these 2 histograms share the same median, the same MAD. So basically, will give us the same robust statistics, but are totally different, because in the first, we have k equal to 1, we have all the data points in the zone, in the interval 1 and 3, and for the second, in the zone 2 and 4. So that was the challenge. We want to have a Markov kernel that lets the median and the MAD unchanged, but to have a Markov chain, to have a Markov chain on our vector, data vector that fully explore our latent space. So the first thing that we did, it was thinking about just resampling one coordinates, but unfortunately, by doing so we just like pick one coordinate and resampling it while preserving the MAD and the median unchanged. But in that case, the value of k and delta would stay fixed. So we don't have an ergative Markov chain. So we thought about a lot about it, and we tried with 2 coordinates, and surprisingly, it works, and we got an ergative Markov chain. So just to make sure, we initialize a vector really naively, and then we just pick randomly 2 coordinates and resampling them while keeping this constraint true. That's it. So if we are looking about our Markov kernel, it's quite ugly, but it's not that complicated. It's just a lot of if and else, of condition, and of a truncated version of our parametric distribution. I will not explain it because it's too long and not that interesting, but I will just show you two cases. So the first one, so let's suppose that we just picked 2 coordinates. So we picked one coordinate in that interval, and we picked the observation that determined the MAD. We can resample the blue observation in that interval. Let's say that we just move in the other side of the MAD, so of the median. So to keep the median unchanged, we will have to change our red observation we will have to switch it to the other side. And then by doing so, we just change the value of delta. It's the same for the value of K. Let's say that we just pick 2 observations in the zone 1, 3. We can resample the blue one on the full support. And if we are lucky enough, so we have like a probability 25%, we'll just like change the apportionment of a vector by just changing the value of K. So if you're not believing me, I can show you this graph. So it shows that even with a really naive initialization, we have a Markov chain that mixed well and fully explore the data space and have reached a stationarity distribution, which is as we can see in the graph. So this graph is the final histogram, and this is the value of K. So we can say that even by initializing K at 0, we'll reach a stationarity, which is basically it's 1/4 of the observation in each interval, because we have a symmetric distribution. Here it's Gaussian, and we have delta, which is changing during the iteration. So basically, it's just an ergodic Markov chain. We're happy with it. So let's quickly see a little data, real data.
Yeah, well,
yeah, tell me.
What I don't understand, like, okay, what is the role of K? K is the role of like.
Okay, basically K is just like controlling the repartition of the data point between the zone, the interval 1 and 3, or 2 and 4. So here in the example,
because you know that like they're gonna be half on the one side, half on the other side, and half on the middle, and so you want to say half.
Yeah.
Okay.
And here in the Gaussian case, K is not really informative, because you know that you have like a symmetric distribution. So you say that you will have like half of your data in each part of the median. So you will just targeting 1/4 of your observation in each interval. But if you have like a non-symmetric with a heavy tail on the right, you will have a K will play a huge role. So that's why it was important to update it at
faster rate. Yes.
Yeah. During the iterations. Okay. So
you know convergence, like the speed of convergence of your
yeah, basically it's so
even empirical.
The speed of convergence, it was something like square root of n.
Okay.
So it's quite okay.
Yeah,
quite standard. So let's present a little real data application. So I randomly pick a commune from France. So there is 35,000 of communes in France, and I randomly pick one, which is Comte. It is the birthplace of my grandfather, but it's totally random. And we want to, so we have some data. As I said, in the philosophy database from INSEE, we have access for each commune to some quantiles of our population. So I think the village have like something like 2,000 inhabitants, and we just want to modelize the income data. So we use like the translated Weibull distribution, which is a distribution that is huge in the literature, and we just like used our insufficient Gibbs sampler, and we got this wonderful distribution. So we just try to consider more and more quantiles. So we had like 11 quantiles in our data set for the small village, and we just tried using 2 quantiles, 3 quantiles, 4, and then 11, and we can see that the more information that we got, the more peaked our posterior is. So that's pretty logical. But the interesting part is that after considering 4 quantiles, we have like basically the same. We don't our algorithm identified the same parameter. So it's like it say that our method converge and identified some parameters. So it's quite a good news. So now, if I have some time, I will just talk about Bayesian model choice, because all I said during this talk, it was about Bayesian inference, but another field of Bayesian framework is about model decision. So basically, when you're a statistician and you want to choose a model, so basically you want to quantify the goodness of the fit of the model to your data. So to do so, we have this marginal likelihood, who was the normalizing constants in my poster in the first slide. I didn't lie. I said that I will talk about it, and it's what I'm doing right now. So this marginal likelihood is used in the Bayesian model choice to quantify the goodness of the fit of one model to our data. So basically, it's just our posterior, but with all the parameters integrated. And if you want to compare two models, so there is a really useful tool that has been introduced by Jeffries a long time ago. You just have to do the ratio of the two marginal likelihood. You obtain a base factor. And basically, if your base factor is quite large, you will choose the first model. If it's quite close to zero, you will choose the second model. It's really simple. But in many cases, this base factor is not available in closed form. So you will have to do some Monte Carlo approximation. And there is a lot of techniques that are used in the literature to approximate the base factor with importance sampling, harmonic mean. But I will talk really fast about one of the techniques that we considered, that was the bridge sampling estimator. So basically, with the bridge sampling estimator, the thing that we are doing is that we are estimating the two marginal likelihood at the same time using some samples of the two likelihoods. So first, we have to have sample from those two likelihood, and then we can have a consistent estimator of our base factor. So that's the only thing that we have to know for now, because I won't do all the proof behind the convergence of the base factor, the bridge sampler, sorry. But now let's go back to our problem. So as I said, in our framework, we don't have access to some data. As I just presented, the base factor is based on data. We don't have any data. The only data that we have is our robust statistics. So we were interested in the literature about the base factor based on some statistics. And hopefully that's a huge part of the ABC literature, because the ABC that I presented first, which is quite used in that case of framework, is also used to do some model selection. So there was this paper from Grollo in 2009 that presents the form of the base factor targeted by ABC model choice. And there was this paper from Jean-Michel Marin and Christian Robert in 2013 that gives some necessary conditions for this base factor based on some statistic to be useful for the model comparison. So for many years, people in the ABC literature was just doing some model decision while estimating something that was not useful at all for model decision. For the thing that is really important to understand is to be useful for estimation doesn't mean to be useful for decision. So that's why there is this conditions given by Jean-Michel Marin, is that for a statistic to be useful in the decision, they have to have asymptotic mean that differs from one model to the other to make sure that everything understands. So they just introduce in their paper this toy model. So we are comparing a normal model and a Laplace model. And as you can say, those models have unknown means, but have known scale parameters. So they just like set the scale parameter to have the same variance and the same moments of order 4 and 6. And they try to do ABC model decision using the median, using the variance, using the moments of order 4 and 6. And they just found that the ABC decision was basically, I don't know. So a base factor, which is more or less equal to 1. But using only the MAD, so the MAD, which is like a scale estimator, an estimator of the scale, they obtain the result that I just present here, is that under the ghost data with different size of model, so it is n equal to 10, n equal to 100, n equal to 1000, the ABC model decision is more and more precise and more and more correct. So they give from an I don't know, I come to a yes or no, which is accurate. So we try to implement the bridge sampler. So just to go back to the bridge sampler, I just to use a bridge sampling, so to have an exact estimator of my base factor in the bridge sampler, I just needed samples from my posterior of the model 1 and posterior of my model 2. With my insufficient Gibbs sampler, I just get sample from the posterior of each model, but under the posterior of the joint law of the parameter and the data. And we can use it in the bridge sampling to have an insufficient bridge sampling estimator. So basically, we just putting not just the parameters that we just sampled, but the joint sample of the data that we sampled and the parameter, and using it in a bridge sample. And we can get some similar results. And the main difference between our method and the ABC model choice is we are just like skipping the ABC error with epsilon greater than 0. So here we just propose an exact estimator, so of the base factor using some insufficient statistics. So just to confirm that our method is working, I just introduce really quickly a second toy model, which is also in the Jean-Michel Marin paper. So here we consider a Poisson and a geometric, and we observing the summary statistic, which is the sum of our data set. This statistic is sufficient for both models. So you can have the sum is sufficient to estimate the parameter of the Poisson and the geometric, but is not sufficient across the models. So you can compute the base factor based on the sum, but basically this parameter won't help you to make a decision, but just to make sure that our methodology estimates this value, we just plot this thing. So in red, you have the theoretical value, and we have our estimations with the box plots. So we can say that our method is consistent. So just to conclude, there is a Python package on my GitHub. You can use the method if you want. This is a method that can be used in a lot of parametric distribution, because the only thing that we have to do is to sample from truncated distribution. So basically with accept reject, we can consider all the continuous distribution. So we propose the method to do some Bayesian inference, but also to perform some Bayesian model choice. And you can also adapt the method to other statistics quite easily. So thanks for listening. And if you have any question, don't hesitate.
Thank you very much.
Thank you.
So are there any questions maybe online? If not, maybe I have some naive questions. Have you tested your model choice for real data and for real?
Yeah, we have this example in the paper using the real data examples for the same village, and we just try to compare two naive models. So it was a log normal and a Weibull, I guess, and we just like put our quantiles in our estimator, running our insufficient Gibbs sampling, and using the sample to have the bridge sampling estimator. And we just, I think for that village, we have like a base factor in favor of the log normal. But it's really naive. You will have that like different value for every data set, but it's a new tool for the statistician to decide which model he prefers in the case that where he observed only robust statistics.
Okay.
So in the Bayesian framework, the only thing that we got before that, it was just like doing ABC model choice, which is an approximation, obviously. And if not, you can do like a QQ plot or something. So it was just to have a new tool and to use it. So it was one new use of the insufficient Gibbs sampler.
Okay. And can you go back to the slides where you presented the methodology that you're not for like for the first part, for when you yeah, that one. Like, I've noticed, do you use augmented data like in afterward here? Do you use augment?
Like it's just augmented data.
Okay,
everything is augmented data.
Okay.
The thing that I'm just observing M and S. Observing the median and the MAD, I created some augmented data, and the challenge is just to update them in my Gibbs while preserving the median and the MAD. So that's why I have these ugly conditions, because otherwise, if I don't do that, I will change the median of the MAD. And I don't want that, because I'm targeting the distribution condition on the median and the MAD. So you have to keep the constraint verified. That's it. Okay.
Well, thank you.
Thank you. Thank you for
there are not any other questions. So unfortunately, this is the last session for the year, but we're gonna start again in September with plenty of new speakers or old ones. So thank you everyone for connected, and see you maybe in Venice. Bye bye.